Hi, in this video, we're going to take a look at estimating a heart transplant death rate for a hospital of interest. Okay, so the situation that we're in is that I, as a statistician, need to estimate the death rate of a hospital for heart transplants. Now, let's think about this for a moment. There aren't that many heart transplants going on, and there's even fewer deaths. In the small data problem, the frequentist approach really isn't that great. Yeah, we can get point estimate and we can do classic statistics, but really this is such small data that the 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 classic methods of frequentists really aren't as good. So what do we want to do? We want to be able to take information from elsewhere, from academic papers, from results from other hospitals or similar to ours, and incorporate this together to get a better understanding of what's going on. That'll establish our prior. Then pull in our data, pull them together. I've got posterior. Once I've got the posterior distribution, I can get a full analysis of the situation. And so I feel like small data is overwhelmingly, absolutely 100% the best use of Bayesian statistics. It gives us a way to pull in additional information to put more with the data that we've got. Now, think about the situation where I had 10 million rows of data. If I've got 10 million rows of data, frankly, I don't need a prior. I don't need to do Bayesian statistics. I don't need to put my time and effort into this because with 10 million rows of data, I know the distribution. So really, to me, Bayesian statistics does a very unique, special, and powerful job in the small data situation. Okay, so the examples that we're going to go through are from Jim Albert's Bayesian Computations with R. Baseball is his website, and here is his page on Amazon to be able to buy the book. I haven't met the guy, but I'm a fan of his work. All right, so let's go ahead and down to it. All right, so consider the problem of learning about the rate of success of heart transplant surgeries of a particular hospital in the United States. So I'm not talking about all hospitals. I'm not talking about, a system of hospitals. I'm not talking about a region of hospitals. I'm talking about my hospital. So as a statistician, I'm only concerned with this one location. All right, well, then I'm not going to have that many observations to work with. So it's going to be hard to trust my results because I just don't have that much. Okay, so we're going to observe the number of transplant surgeries and we're going to observe the number of deaths within 30 days of the surgery. Why? In addition, one can predict the probability of death of an individual patient. This prediction is based on a model that uses information such as patient's medical condition before surgery, their gender, and their race. Based on these predicted probabilities, one can obtain an expected number of deaths denoted E. All right, a standard model assumes that the deaths follow a Poisson distribution with mean E times lambda, and the objective is to estimate the mortality rate per unit exposure, lambda. So I want to know about lambda, about this death rate. All right, so the standard way that we would go about this using frequentist statistics is I would use maximum likelihood y over e, and that would be what I've got. Unfortunately, this estimate can be poor when the number of deaths is close to zero. And well, fortunately, it is close to zero. Unfortunately, for me, for a statistician, this is a tough problem for me to get a good, reliable estimate. So in this situation, when small death counts are the norm, it is desirable to use Bayesian estimates that use prior knowledge about the size of the mortality rate. All right, so this part of Jim Albert's text is I feel like he didn't do the best job on this on explaining this one part. So I copied and pasted most of this from Jim's work. But for what we're going to do we're going to start with a non-informative prior. Now, why are we doing a non-formative prior? Because I don't want to bias anything. So a non-formative prior is exactly that. Doesn't give us much information. Doesn't it doesn't swing our model away from the data. It's there basically it's there just to set up so I can execute Bayesian statistics. Now, I'm going to set up this non-formative prior. Then I'm going to go and I'm going to do my research and I'm going to look around and see what's going on in terms of other hospitals across the country, in the region, my network of hospitals. Hospitals are similar to us. And as I go through this process, I say, hey, you know what? I'm going to say that the gamma distribution makes sense for lambda. So we have gamma of alpha beta. Alpha is the shape and beta is the scale parameters. And so this is going to be what we're driving at when we say gamma distribution. Now I'm going to collect data all of from academic papers, from reports, from news articles, from experts. I'm going to get the number of deaths at each hospital, the exposure number of surgeries at each hospital, and we're going to have 10 hospitals. And then I'm going to estimate it like an overall death rate across the country and an overall death rate at each individual hospital. And so what I've done here is I start out with this is my initial prior of the non-formative 1 over lambda, which you'll notice is not actually a probability distribution. Then I'm going to combine it with the information that I get from doing my research. All right. And so then putting that all together, I'm going to get this set up. And so now this is my prior before I get my data for my hospital. So there's a prior, just my non-formative prior before I get any data whatsoever. Then I get data that's not my hospital, but it's available to give me further insights. I put those together to get a new distribution, which will be the prior when I actually collect the data for the hospital I'm interested in, and that's this one here. So at this point, we've had uh, you know two different priors going on. All right, so we're going to set alpha equal to the sum of the deaths. We're going to set beta equal to the sum of the surgeries. And then, for the example in the textbook, we've got 16 deaths and we've got just over 15,000 surgeries. And so as my prior, before I look at the data for my individual hospital, is going to be gamma 16, then 15,174 as the prior. Okay, so now I'm going to go to my actual hospital and start collecting some data. I'm going to take the observed number of deaths from surgeries, Y obs, and for a given hospital with exposure E, it's Poisson E lambda, and lambda is a gamma random variable for the prior. Then my posterior distribution will be gamma with these updated parameters. That's going to be alpha plus the number of deaths, beta plus E. Also, the prior predictive density of Y before any data observed can be computed using this formula. Notice the conditional probability aspects going on, where F given lambda is Poisson, E lambda, sampling distribution, G is the prior density, and G of lambda given Y is a posterior density. Both the posterior density, G of lambda given Y, and the predictive density, F, play an important role in the Bayesian analysis. By use of the posterior density, one performs inferences about the unknown parameter conditional on the Bayesian model that includes the assumptions of sampling density and the prior density. One can check the validity of the proposed model by inspecting the predictive density. If the observed data, Y observations, is consistent with the predicted density, then the model is going to seem reasonable. If y obs is in the extreme tail of the predictive density, then perhaps the prior density and the sampling density have not been specified well. And maybe I want to back off and reassess the situation. All right, so now let's consider some inference about the heart transplant rates of two different hospitals. One that has experienced a small number of surgeries and a second that has experienced many. Okay, so hospital A has y-obs equal to 1 and exposure of E equal to 6. Okay, so now, actually that should be expected value. All right, so here is my prior. Here's y-obs. Here is the exposure, and then here is the possible number of deaths. So now let's look at the probability distribution for the number of deaths that we would expect to see here. All right, so I need to make this a touch smaller. We can see that overwhelmingly we're expecting to see 0, but it's a non-zero probability. It's about 6% chance of seeing one death, and very small but non-zero probability of seeing greater than one death off of this many surgeries. Now let's modify this. Let's change this up now so that our data is for 4 deaths and E is equal to 1767. When I look at the probability distribution of the counts of deaths, now you can see it's a little bit more complicated, right? A lot more surgeries going on. So realistically, there's going to be, there's more opportunity for more deaths, unfortunately. And so now we have a more of an evened out distribution going on. One death is the most likely result, then followed by 2, then 0, then 3. And you can see it's a skewed right distribution. All right, to see the impact of the prior density on the inference, it's helpful to display the prior and the posteriors on the same graphs. So let's do that. Okay, so what I've done here, let me back up. All right, I'm going to go and I'm going to go through and get the distribution of reasonable rates for each of these. So here, this is for hospital A. Here is the histogram of what I would have for a probability distribution for the lambda rate. And the black line is the prior, the blue is the posterior. So we can see that compared to other hospitals across the country that we considered similar to our own, we're actually doing a little bit worse. That's not good. If we would have had, if our hospital would have been doing better, the blue distribution would have shifted to the left, having a lower rate for the distribution. So it's not a huge difference, but this indicates that it's slightly worse than like that national average aspect for those 10 hospitals. Now let's look at hospital B. Now it's like, oh wow, that's more of a shift to the right than I had before. Okay, so the black is it's the prior. The blue is the posterior. By shifting to the right, that's an indication that, well, the hospital in question, hospital B, has a higher death rate than the ones that we included in our prior in our analysis. All right. So we can use Bayesian statistics to handle small data problems very, very well, and we can get very complete representations of situations that we can't get with other models. I feel like this is the best use of Bayesian statistics, period, the small data problem, because we can get some information, get educated on what's up, convert that into a mathematical statement, combine that with data, boom, I've got something great. All right, well, that's all I've got for you. Life is short. Do math.